All right, well, here we are again. Today we're going to be talking a little bit about Section 4.3, which previously Section 4.1 was talking about the law of sines. Last section we were dealing with in Section 4.2 the law of cosines and area. Section 4.3 is a complete departure away from those things. Well, it feels like it at least. We're going to be jumping into and talking about vectors. Now, here's the thing about vectors. Um, a lot of the applications involved in vectors are incredibly important. In fact, the majority of the physical sciences and physics, um, and trying to understand the way in which force operates or work is being used, any kind of quantities. Astronomy, it's huge in. If you're measuring gravitational impact between multiple bodies, you use vectors, and sometimes it's a little bit more complicated than just straight line vectors, although that's really what vectors are. It's just straight line forces being applied. Now, the cool thing about this is the math actually isn't really that crazy compared to the stuff that you've done. It's just a lot of the notation is new. You maybe have never seen anything like this before. So hopefully, our time together, I'll be able to walk you through this. So a vector is just a directed line segment. Those line segments have a magnitude associated with them. So if you were to go ahead and graph vectors, um, let's say you're using a traditional Cartesian coordinate system, so an xy axis. Vectors are always going to be coming off of the origin, and they're going to be going towards a specific point. So they have an initial point and a terminal point. I shouldn't say always coming off the origin. In most cases, what you'll see is, given the problems that we'll be dealing with here, you will have your initial point being set as the origin, and the terminal point will be generally given to you. Okay, so vectors can be named with a single letter. They can have so it can be a letter with an arrow over the top of it, just indicating there's direction or force being applied. Or the vector itself could be in bold, like I have listed here. So you can have two different points, where you have a vector going from your initial point A to your terminal point B, or it's just V as in that's the entire vector itself. So the notation that we use for the magnitude of that vector, we have these two vertical lines on both sides of the vector itself. You can call it that with the line over top, or you can just do it without. It's still going to be known. Or you can do the two vertical lines on both sides with your bolded typeface in the middle. In both cases, or I should say in all of three of these cases, you're always going to have the vertical lines indicating the magnitude of your particular vector. So a scalar is just a real number used to indicate the magnitude of a measurement. So in a sense, you're just indicating, hey, take that vector, multiply it by a certain amount. In a sense, you're either doubling or tripling or quadrupling or whatever multiplier or coefficient you want to call it. Essentially, that's what a scalar multiplier is. It's just a coefficient that's being applied to your vector that's increasing the magnitude by that amount. So in this case, you have the vector multiplied by a number. You have, for example, 3v, right? That would be 3 times the amount of the vector. If we have equivalent vectors, they have the same magnitude and direction. I mean, that's pretty apparent. The resultant vector is the sum, so when you take two vectors together and sum them up. By the way, there are, just for the sake of my sanity and probably yours, I would encourage you to go and read through this entire section. There are so many good graphs listed, and just all different kinds of pictures just to really help you understand exactly what it is that we're working with. So the resultant vector is the sum of two vectors. You can do a couple of different things. There's a triangle method or parallelogram method. Take a look, please, at these figures. They're at the bottom of 313. I'm actually looking at them right now. They're really, really good and help you get a good grasp of what it looks like. All right, so if we're given that v is equal to AB, A and B are the components of the vector. You can actually think of these as like kind of like an XY point. So this could be like an X coordinate. This is a Y coordinate, but there's a line that is running, and like I said, it's generally from the origin to those particular values or those particular quantities. Whatever the quantity of A is or the quantity of B. Okay. Here's some fundamental vector operations. So if you've got v is equal to, your vector v is going to equal the components a and b, and w is going to equal the components c and d. K is a real number, so they're probably going to use this as a scalar down below, which is what they do. Then what we have is the magnitude of v is going to just be the square root of those two components. So you can think of the x and y coordinates as being, it's kind of like in the Pythagorean theorem, you're solving for that last missing piece. That's really what the magnitude of this vector is doing, is you're solving for the missing component in the Pythagorean theorem. V plus W, so when you sum those together, you add just the components, the individual components, the corresponding components. So A plus C and then B plus D right here. And then when we have a scalar multiplier times the components, we just multiply that out times each of the individual components themselves. So it's, again, pretty straightforward. A unit vector, so it's a vector with a magnitude of 1. Now, here they have I and j. These are mostly what is, it's probably the most common way of writing these unit vectors. The unit vectors are just going to be 1, 0, and 0, 1. Those are the components of them. You can actually, if you're given any non-zero vector v, you can find the unit vector by dividing each component by the magnitude. So we'll go through a couple of examples of this. You'll see how that works. It's the math is actually pretty straightforward. It's again, this is a lot of just new stuff maybe that you've never seen before, and I get that. How it actually practically works out is it's something that's probably very familiar to many of you. All right, so here are some of the things that I do want to draw attention to. There are like a bunch of different things here that are listed on all of these pages, and I listed them out, and the reason why is it's just way too much for me to put in the notes. I really encourage you to go back and take a look at all of those. There's some really good examples, especially when it comes to questions on the homework assignment. And so what I'm going to do now is I'm going to go through just a few examples, kind of hopefully give you a good idea as to what is needed to solve some of these problems. Okay, so let's go ahead and switch over to our whiteboard here. And now what we're going to do is we'll go through just a few problems. Let me go to the right page here so I can read the directions. Question number 6. Okay, question number 6 is going to be asking us, find the components of the vector. So remember, it's like your AB components with the initial point P1 and the terminal point P2. Use these components to write a vector that is equivalent to P1, P2. Okay, so here's what we're doing. So we're given P1, so this is like a vector, okay? Well, actually, it's really just a point, and we're trying to find the vector. So P1, the point is going to be 5, negative 1. And P2 is equal to the point 3, 1. Okay? So now what we're going to do, let's look at the A component and B component. The A component is just going to equal each of the individual x values here, one subtracted from the other. So we'll do the second one first. It doesn't really matter, honestly. I think it's going to be completely fine. Well, actually, I think it does in this case. P1, yeah, P1 is actually going to be the initial point. So you actually do have to start with the terminal and then work your way to the initial. So yes, the order does matter. This is going to equal -2. B is going to equal 1 minus a minus 1, which is going to equal +2. So what we have is P1, P2 is equal to, and here's the components, -2, 2 for my AB. So that vector right there is our solution. And you can actually rewrite this if you want as V with your little arrow over the top. Okay, it's hard to, this is one of the things that I was realizing. It's nice in textbooks when they can boldface certain things. You can't really do it when you're working on a whiteboard or on homework assignments, so I just always use the arrow to indicate my vectors, and I've always done that. So that's probably what you'll see from me just moving forward. When we start to get into the unit vectors, I'm probably not even going to write the arrows over the top. I'm just going to assume you know exactly what I'm talking about, and part of the reason why is you are spending more time drawing arrows than you are on actually doing the math. So, and I obviously don't want to do that. So, so we'll take it by ear. All right, question 14. So this one is asking us to find the magnitude and direction of each vector, and also find a unit vector in the direction of the given vector. Wow. Okay, so there's a bunch of things here. So we need to find the magnitude and direction, and we need to find the unit vector. So they give us that V is equal to the components -50, and you'll see my little component thing, or my my brackets are terrible for vectors. I never really figured out a good way. Like, sometimes I go too far, sometimes I'm a little too short. It's just, you know, this one's like way off. So just, you know, great at drawing. That's why I jumped into math to begin with, right? It's to learn how to draw. All right, so we're looking for the magnitude of V. So this is going to equal, and all we're doing here is this is going to be the square root of our components. So it's going to be -50 squared plus 30. Remember, it's like the missing piece of the Pythagorean theorem. This is going to work out to being 10 times the square root of 34. And I'll just approximate this. This is going to be 58.3. Okay. So that is the magnitude of our vector V. The direction, this is going to be the next part. Now there's a note, if you look back on one of the examples, so let's see here, where the heck is it? Bear with me. Okay, so on page 314, 315, there's a really solid example that kind of works through how to find the magnitude and direction. I just did the magnitude. The direction, you're actually going to be using tangent because it's the opposite over adjacent components. But in this case, we're looking for the angle, which means we have to use the inverse tangent function. So in a sense, this is what we have. We have alpha is equal to, you can use theta, it doesn't matter. I don't know why I just said alpha, because that's what the book uses. This is going to be the absolute value of 30 over -50. And this is equal to inverse tangent of 3/5, which is equal to, well, I'll approximate it. You can do this in a device, but your approximation is going to be roughly 31 degrees. Okay? So now that we have what alpha is, one of the things we know is that this is going to be, we need to use a reference angle because we've got a negative component associated with it. So the reference angle is going to be 31 degrees. So theta is going to be 180 minus 31. Think about it like this. If this is my vector, you can think of this as being in the second quadrant. So we're looking at the direction based upon the angle off of the x-axis. So we need to measure the angle from the x-axis. Well, essentially it's the angle from the x-axis from 0 degrees all the way up. And this right here only gives us the other one. So it gives us the angle from the x-axis up to the vector in the second quadrant. So we actually need the opposite side. That's why this is the reference triangle, or the reference angle, I should say. So this is going to be 149 degrees. Okay. All right, so we still have one more piece. We need to find the unit vector. So the unit vector is going to be u, and it's going to equal, what we do is we actually take the components and we divide it by the magnitude, and that's it. That's literally all we do. So this is going to be minus 50 all over the 10 root 34, 30 over 10 root 34. Okay, so this is equal to negative 5 root 34 over 34. I guess if you want to rationalize it, you can do that. And then this is also going to be 3 root 34 all over 34. Okay, so that is your unit vector right there. All right. That's question 14. Let me jump ahead to the next one. Again, this is a lot of the math. You guys already know how to do all this stuff. It's mostly just applying it in a different way, and that sometimes can be the tricky part, because you may be kind of used to doing things a certain way, but in fact it's just kind of changing it up a bit. All right, so question 26. Question 26. So this is asking us to perform the indicated operations where the vector u is equal to the components minus 2, 4, and v is equal to minus 3, minus 2. Okay. So what we're doing is, in this case, we're looking for the magnitude of v plus 2u. So first, before we do the magnitude, let's just find what v plus 2u is in terms of its components. Then we can go ahead and find the magnitude. You need to have the components before you can do the magnitude. So we've got v plus 2u is equal to, so we're going to take this guy, minus 3 times minus 2 plus 2. So this is a scalar quantity times minus 2, 4. Scalar multiplication. This is the same thing as, let me just rewrite this out, minus 2. And then I just take the 2 and I multiply it by each of the components. So now I'm adding, this is going to be minus 4, 8. This is equal to, at this point now, we take the individual pieces and add them up. So we'll have minus 3 minus 4. And the second piece will be minus 2 plus 8. Oops. Plus 8. So this is all going to work out to be a minus 7. What is this? Minus, or positive 6. Okay, so that's our vector. And now, or our resultant vector, I guess is what you can call it. So now what we have is we need to find the magnitude of v plus 2u, which is equal to, the square root of those, the sum of those components squared. So minus 7 squared plus 6 squared is equal to square root of, this is going to be 85. Okay? And that's our final answer. You can simplify that if you want. Actually take the square root of 85 and put it as a decimal. I don't really care. It's completely fine for me. So that's question 26. Question number 36. Okay. It's a similar idea. We need to find the indicated operations, and now they give us, in this case, the unit vectors that we're working with. So it's a couple of different unit vectors, the sum of two unit vectors. So here's where I'm not going to draw arrows anymore, okay? I'm just going to assume you realize that these are not variables, these are vectors, so just bear with me, okay? I'm not going to draw the arrows anymore. U is equal to 3i minus 2j. And v is equal to minus 2i plus 3j. So we're asked, so these are what's given, and we're asked to find 2v plus 3u. And we also need to find the magnitude of that. So let's start with that. 2v plus 3u is equal to, so 2 times minus 2i plus 3j plus 3 times 3i minus 2j. Okay, now what we need to do is, these are scalar quantities that are multiplying by these unit vectors. So essentially, all you're going to do is just distribute this 2 across the board. So this is going to be a minus 4i plus 6j. And then we'll do the same thing over there. I'm just going to put it in brackets to indicate the correct each component. So this will be 9i minus 6j. Okay? And now what we do is we combine the components, the scalars that are in front of each of these unit vectors, together times that unit vector. So now this becomes a minus 4 plus 9 times I plus a 6 minus 6 times j. And what we get is that's actually going to be 0. This is going to be a 5i. Okay? And again, that is a vector. I'll put the vector right there. So now we need to do the magnitude. The magnitude is going to be the 2v plus 3u. This is equal to the square root of 5 squared. So you can think of this as being, if you want, 5 times 1, 0. Okay, and this is the same thing as 5, 0. So that's technically what we're working with here at this point. 5i is just going to be 5, 0. Plus 0 squared, this is equal to the square root of 25, which is equal to 5. So, interesting comparison between these two. Which makes sense. I mean, the magnitude, if you have a unit vector of only one, the one component of that unit vector should only be exactly what the scalar is. That makes perfect sense. Okay, let's move on to the next question. So that was question 36. Now we'll do question 62. We got a few more to go, and we will be done. So again, I'm not drawing any of these arrows. Bear that in mind. There's going to be a lot of arrows moving forward. So now we're looking at the dot product. The dot product of these vectors. So v is equal to minus 4i plus 2j. W is equal to minus 2I minus 4j. By the way, I don't know if you realize this. These are just a different way of representing the components. So previously we had, I mean, I guess if you wanted to rewrite this, this would be the same thing as minus 4, 2. Okay, and this would be the same thing as minus 2, minus 4. It's just another way of writing it, that's all. So just bear that in mind. Okay, so now what we're going to do is we need to find the dot product. So the dot product, this is going to look a little different. So we've got V times W, the dot product of V and W. We're not multiplying. It's going to be, again, because these are not variables, they're vectors, it's going to look a little different. So what we'll do is we'll just go ahead and write this all out. 4i plus 2j dot product of minus 2i minus 4j. Okay. When we do the dot product, we actually are just going to multiply the individual components times each other. We're not doing FOIL on this. Okay. Again, this is the distinction between a vector and a linear function. Previously, maybe you had two linear functions you were multiplying together. These are two vectors, so it's essentially what we're going to have is minus 4, so this component times that component times minus 2, and that's going to be the I component. Or I'm sorry, this is not, the dot product is not going to create a vector itself. It's actually just going to be a number. Sorry, let me backtrack. Minus 4 times minus 2, and I'm adding a 2 times a minus 4. Okay? So this is the same thing as 8 minus 8, which is equal to 0. So now here is something interesting. I don't know if the book actually says this. At least I didn't see it in there. Let me just take a quick peek back through. No, I do not see it. I'm surprised that they wouldn't include that. So when you are taking the dot product of two, well, actually, okay, so it is on yeah, okay, it is. This is on 323. So this is the condition for perpendicular vectors. Two non-zero vectors V and W are orthogonal. Orthogonal is kind of like another word for perpendicular. There's some historical context behind it. I'm not going to get into that. They're perpendicular or orthogonal if and only if V times W equals 0. So in other words, we've got these two things multiplied out. They equal, the dot product is going to equal 0. So my camera just shut off, so give me just 1 second to get that back up. So when we have the dot product between those two equals 0, that means that those two vectors actually form a right angle with one another, 90 degrees. So that's just kind of a little side note. So that's our solution for question 62. All right, question 68. They are asking us to, in this case, scroll over here, to find the measure of the angle between the two vectors, state which pairs of vectors are orthogonal, round approximate measures to the nearest tenth of a degree. Okay, so the nearest tenth of a degree. So 68, they say that V is equal to 8I plus J, and W is equal to minus I plus 8J. Okay, so here's what we have. We need to find the angle between these. So to do that, there's actually a cool example back, I believe it's on page 322. We actually are going to use the cosine of just a few of the different components. So the cosine of the angle is actually equal to the two vectors, the dot product of the two vectors divided by the multiplied magnitude. So let me write this out. So we're going to have cosine of A, or cosine of alpha, we'll just call that, is equal to V dot product W all over the magnitude of V times the magnitude of W. Okay, and I'm not going to put the dot in there just so you understand that this is multiplication. So here's what we're going to do. We'll do the dot product at the top. So this is 8I plus j times minus I plus 8j. Okay, all over the magnitude of V and the magnitude of W. So the magnitude of V is going to be the square root of 8 squared plus 1 squared. And then we're multiplying that times the minus 1 squared plus 8 squared, okay, for the second one. So the magnitude of W is just going to be that. All right, so now if I were to work this all out, I'm going to get the dot product of these two, so 8 times a minus 1 plus a 1 times an 8. So the 8 times the minus 1 plus the 1 times the 8. Again, we're not foiling. It's a dot product, so we're only multiplying the matching components up. This is going to be divided by the square root of 65 times the square root of 65. And this actually works out to being 0 over 65, which is equal to 0. Okay? So in other words, we've got that cosine of alpha is equal to 0. Another way of thinking about it is you're looking, alpha is equal to the cosine, the inverse cosine of 0. Okay? This should be one that you can actually easily find. If you go back to the unit circle diagram, told you, it always comes up. You can find, again, the x component that is going to produce a zero. So in this case, if you actually were to go and work it out, this would be 90 degrees. Okay. So cosine of alpha in this case is going to be 90 degrees. All right. So that is that question. All right, last question here. Question 76. This is V. Let me just write down the question. 76, V is equal to 5I plus 2J. And W is equal to minus 5I minus 2J. And they want us to find the projection. So we're projecting one onto another of V onto W. So that's how you read it. The projection of V onto W. It's kind of like if you think about logarithms or, yeah, I mean, really, I guess logarithms would be the way to do it. The logarithm of, say, 10 base whatever. It reads exactly the same way. It's just the way that we say it is pretty similar. So there's a formula for this. This is equal to the dot product of the two vectors. So V times W all over the magnitude of, in this case, W, which is what we're projecting it onto. So this is going to be the magnitude of W. So this is the same thing as let's go ahead and multiply these. Let's write these out. The dot product. See, I'm catching myself saying multiply because it's not. It's a dot product. Minus 5i. Once you get into the habit of saying that, it's hard to get out of it, right? So this is going to be the absolute value of absolute value. The magnitude of W. This is not a very common topic. I'm so used to using absolute values with all my classes, so this is kind of new. So this is, let me go ahead and write this out. I'm not actually doing the magnitude here. So the magnitude is just going to be the square root of minus 5 squared plus a minus 2 squared. Okay. All right, so now this is equal to 5 times minus 5 plus 2 times a minus 2 all over the square root of, what, 29? So now we've got 25 minus 4 all over square root 29. So this is equal to 21. Oh, wait a minute, hang on. Oh, that's a minus. Minus 25, minus 24, minus 29 over root 29. And then if you rationalize this, you'll find that this is going to be minus root 29. Okay? And so this is approximately, because I think they were asking us to round to the nearest tenth of a degree. Or, yeah. Well, it's finding the projection. I'm just going to round it. There's no reason why we can't. This is going to be 5.4. Okay. So that's that question. That is pretty much, I guess, vectors. There's a lot in the textbook, like I said. It's probably going to take a little bit of time to grasp how all of it works. And I think if any of you go and take a physics course in the future, this is a pretty common topic that comes up. In astronomy, this is definitely a topic that's going to come up as well if you take an astronomy class. So right now, this is just kind of the fundamental basics of how you do certain, I guess, I don't even want to call it applications, but how you do some of the operations, I should say, of vectors. So if you have any questions, let me know. I'm going to shoot out a review here shortly for the exam, and I'll go ahead and give you a few days to work on that. So actually, I might not do that. I might just shoot out the exam and give you a few days to work on the exam. I don't know. We'll see. Anyway, have a great one, and if you have any questions, let me know.